Good morning, good afternoon, and good evening, everyone. Thank you for joining us today. My name is Allie Kane, and I will be the moderator for our presentation. I lead the implementation side of Fluor's business transformation and innovation team. We focus on new ideas, never losing sight of the critical thinking and analysis that comes from our global team of expert engineers and designers. Our people are at the core of our success. As with the other webinars, this will be a technical presentation intended for managers of owner-operator companies with facilities that require industrial water usage. Today, subject matter experts Joe Guida and Burcu Ekmekci will talk about Fluor's integrated water solutions. Joe and Burcu will explain how water reuse and recovery strategies can be identified and incorporated for a client's new or existing facility. This approach helps clients achieve greater water sustainability by reducing stress on local water resources, minimizing effluent discharge, and optimizing overall life cycle costs. So this morning or afternoon, we actually have 3 subject matter experts with us. I'll introduce our main speakers, followed by our health, safety, and environmental topic speaker. First, we have Joe Guida. Joe has over 40 years of experience in the operation and design of industrial and environmental systems for various industries and has been recognized as a Fluor Fellow. He is a registered professional engineer in Texas, Louisiana, and Florida, and holds a bachelor's degree in chemical engineering as well as a master's degree in environmental engineering from the University of South Florida. He enjoys giving back to his alma mater, where he has served as an adjunct professor since 2018 and teaches a course on ethics and process safety and design for senior chemical engineering majors. Joining Joe is Burcu Ekmekci. Burcu is a senior process engineer based in Fluor's Amsterdam office. She has over 15 years experience in design and operation of industrial water and wastewater treatment systems in refinery and petrochemicals, food and beverage, pharmaceutical, and the chemical industries. Burcu has the in-depth knowledge and skills to develop a project from concept to reality. Over the years, she has led several projects ranging from feasibility studies to detailed engineering and has been involved during the startup, pre-commissioning, commissioning activities, and troubleshooting of a wide range of units. Burcu serves as a vice chairwoman for the Netherlands-Belgium section of the American Institute of Chemical Engineers. She holds a master's degree in environmental engineering from Wageningen University in the Netherlands. When she's not working, Burcu enjoys classic ballet dancing and spending time with her 3-year-old daughter, Sophie. And finally, for today's health, safety, and environmental topic, which really is going to set the stage for our webinar today, I'd like to introduce another one of our water subject matter experts and consultants on this presentation, Tamim Papalzai. Tamim has over 21 years of experience in the design and operation of industrial water and wastewater treatment systems in a wide range of industries, such as oil and gas, petrochemicals, power, infrastructure, and renewable energy. He has a diverse background with experience in various phases of project development, which include business development, feasibility, detailed design, project management, startup and commissioning, and troubleshooting. Tamim holds a master's degree in civil and environmental engineering from Norwich University in Vermont. He loves volleyball, water sports, and spending time with his family. So now to get started, I'd like Tamim to please unmute his line and share the brief HSE topic with us.
Thank you, Allie. As Allie mentioned, I'm going to start off this discussion with a safety topic that I think is relevant to the discussion of water sustainability. Since 2009, global leaders in business, academia, government, and NGOs have met to identify and discuss the most pressing global business risks. The World Economic Forum, WEF, has repeatedly identified the water supply crisis as the top 5 global risks in terms of likelihood and impact since 2012, as highlighted on the slide. Water crisis is defined by WEF as a significant decline in the available quality and quantity of fresh water, resulting in harmful effects on human health and/or economic activity. The world withdraws approximately 4,000 billion cubic meters of fresh water each year, which is roughly equivalent to the volume of all the fresh water in Lake Michigan. Now, this is 3 times higher than what the global community withdrew over half a century ago. Water withdrawals are increasing at a rate of 1.6% per year. Global demand for water is predicted to increase by at least 30% between now and 2040. The majority of the new demand is driven by agriculture, which makes up for 70% of global freshwater use. Food production is expected to grow by 2040 in order to provide food for a larger population, which will in turn increase agricultural water needs. Currently, the energy sector, which includes fossil fuels and biofuels, consumes about 10% of global freshwater withdrawal. However, since the global energy demand is on course to rise by 2040, that will also increase the energy sector's water consumption by approximately 60%. Such an increased demand presents a mounting challenge to meet the global population's water needs. Currently, in several areas of the world, there is already insufficient safe water supply to the local residents, primarily because of population growth, unsustainable industrial water withdrawals, and poor infrastructure and governance. This increasing imbalance of water supply and demand is a problem all industries contribute to and face operational risk from. Realizing this, businesses are naturally considering water scarcity as a significant risk factor when making business investment decisions. As can be noted from the water stress map, businesses are directly impacted by the limited resources across various regions. Water stress measures the ratio of total water withdrawals to available water supplies, which includes surface and groundwater. Water withdrawals include domestic, industrial, and agricultural uses. Higher values, shown in the darker colors, indicate higher water stress and therefore competition between users. Some pertinent questions that may be asked for existing and planned projects include, is there water stress in the vicinity of my project or in the near term or in the future life of the project? What are alternative ways my project can reduce the amount of water consumption? What are the water reuse opportunities for my project? What are the life cycle cost impacts for importing water from various sources? What is the current and future regulatory landscape that may impact my project's water demands? How can I implement water reuse in my facility? As a responsible business, Fluor seeks to help clients advance water sustainability initiatives to ensure project success in all phases of a project and promote sustainable development and building a better future. And now I turn it over to Joe, who will address some of these important questions in more detail.
Thanks, Tamim, and I'd like to thank everyone for taking the time to attend this presentation today. Today we'd like to talk about industrial water usage. Specifically, we'll be discussing the bullets that you see on the slide. We'll talk first about the primary considerations for industrial water selection and usage. Next, we'll discuss how you can achieve efficient design and integration into the facility. And then we'll have an example of how water scope can be impacted by a process change. The Fluor Corporation is involved in a variety of projects, as indicated on the slide, and we work on the process systems as well as water and utilities systems. So this gives Fluor a good understanding of how to integrate water most efficiently into the overall facility design. The scope of projects that Fluor works on may range in size from thousands to billions of dollars and from grassroots facilities to small modification. But in general, the common thread for most of these projects is that they impact the water systems of the community in which they are located. And we also find that the water systems can have an impact on the profitability and viability of the overall endeavor. As process engineers specializing in water applications, our focus is supporting the viability of projects by developing water and wastewater systems that balance cost of ownership with intake and discharge constraints. When developing a facility design, we have a hierarchy of priorities that must be balanced, as shown on this slide. First, we need to understand the project drivers and how to prioritize them. Next, we need to understand the environmental constraints that will affect permitting and the local community. Lastly, we have to decide on the treatment technology needed to satisfy the drivers and other constraints. We begin with project drivers: cost and schedule, risk, and water sustainability. Capital cost and schedule are usually the first things that come to mind when we think of project execution. However, projects are increasingly driven by life cycle impact, permitting, and a broader view of project risk. Project water scope can include some of the following: facility capacity. Where water constraints exist, potential production constraints exist. If we can reduce the intensity of water use with respect to production, we can reduce the potential production risk. With respect to schedule, I think we're all aware that revisiting project decisions and revising designs once issued can cause a cascade of delays. So it's important to understand the source water availability and quality, along with wastewater permitting requirements, as early as possible. For instance, the source water may not be fully defined as far as composition and variability goes. Does the project have time to undergo a sampling program? Most likely not. So how good is the data and what risk is there in using it? As for cost, water systems have traditionally been considered a cost rather than a profit. But sometimes you can recover valuable residuals such as biogas, reused water, and other products. So we look for opportunities to produce something valuable to allow the wastewater system to offset some of the cost. Project risk may apply to the project execution or to operation over the lifetime of a facility. This can often arise from uncertainty in basic information. Is the climatic information accurate? How rigorous is the underlying sample data? How are governments approaching water regulation in the project region and elsewhere? It's difficult and often impossible to see into the future, but understanding where the risks lie and their consequences is the first step in developing mitigation strategies for the lifetime of a facility. Let's talk about environmental constraints. Every facility has interfaces with the environment. Availability of resources, current and future regulations, and compliance are all areas that must be fully defined. Water sources. In general, the trend is for there to be more constraints on water consumption and more limitations on effluent quality and quantity. So we need to consider alternate sources of water and destinations for effluent. Screening of the available water sources at the site should start early. Things to consider for the screening process are availability. Is there sufficient availability to satisfy demand during all seasons, potential periods of drought, projected future demand? And then there's quality. What is the water quality and how stable is it? Does it change seasonally? We are most interested in suspended solids, dissolved solids, silica, chloride, and organic matter, since these can lead to fouling, scaling, and corrosion. Cost and energy. Having a good basis for availability and quality allows you to design a system that optimizes cost and energy while achieving the project goals. Compared to other sources, surface water is usually the most cost-effective option. Availability of surface water varies from location to location, and it should not be assumed to be available in sufficient quantities. Typical contamination includes suspended solids, organic matter, silica, and residual dissolved solids. These waters are not typically difficult to treat. However, variability in composition due to weather and seasonal conditions require robust designs with multiple design scenarios. Surface water is often the lowest cost for treatment. Well water can range from fresh water with very little suspended solids and organics to brackish water with a wide range of both. Brackish water may be more available, but will be more expensive to treat compared to fresh water. Significant treatment is required prior to removal of dissolved material. High dissolved solids concentrations translates to high energy requirements and potentially high waste disposal cost. Seawater will require similar treatment to brackish water to remove salts, but it will be more costly and energy intensive. Benefit being that it is available in significant quantities. Treated domestic wastewater is now routinely being considered as a source of water. This water is comparable to freshwater sources in many regards, but contains enough salts to require additional treatment, such as ultrafiltration or reverse osmosis. In some cases, it can be used directly for cooling water makeup. In most locations, this water is readily available. However, it could become more scarce in the future as demand increases. Lastly, industrial effluent. The quality and availability will be entirely dependent on the industry. It may require low levels of treatment depending on the waste quality and user requirements. In some cases, it can bypass treatment altogether prior to use. It's important to realize that this will introduce complexity to the design, as a source facility may have excursions in composition and availability during periods that may not always align with the operation of the consumer. This is a decision that comes down to a trade-off between cost, resource availability, risk, permitting, and environmental impact. In general, Fluor will recommend reuse of industrial wastewater if it is a good fit. Cost and risk will always be greater, however, so there must be offsetting benefits to drive this decision. Treated wastewater destinations look similar to treated water sources. Surface discharge will typically be the least flow constrained destination, but will have the most stringently controlled effluent quality. Ocean discharges are typically less stringent, but will be region dependent. It's worth noting that compositions can be regulated by end of pipe composition or the relative effect on receiving stream at the edge of the dispersion zone. For sensitive or heavily impacted bodies of water or those used by the public, the regulating agency may limit discharge. These are known as water quality-based effluent limits in the United States. Understanding this regulatory approval process will be important for managing risk over the course of project execution. Freshwater aquifers may be a destination where treated effluents can balance other consumption, but the treatment requirements can be very strict compared to surface discharge. One other downside of well injection is that drilling and testing of a new well for capacity takes time and money. Consequently, this project expense will likely be approved only once the design has matured to an acceptable level, and this should be captured as a project risk. Deep well injection is an alternate well destination that will be far below the drinking water aquifer, usually at depths to 1,000 to 2,000 meters or more. This destination has less stringent effluent composition requirements because it is an otherwise stranded resource. The limitation here is that energy is required to pump water to these depths, and the wells are more expensive to develop. This method is limited to the geologic characteristics of the region and is not popular with permitting agencies and the general public. Another concern is the pressure stability. This can be affected by scaling potential of a water, variations in salinity, dissolved gas, microbial content, suspended solids, and oil. Industrial reuse is perhaps the best destination for wastewater since it can stay within the plant boundary. But as mentioned earlier, there is complexity introduced as demand may not always align with effluent rates. Technology requirements. Once the water source and discharge locations are defined, it becomes necessary to determine what treatment technology will be most effective to achieve the water quality requirements. In addition, for very large complexes, methods such as water pinch analysis can be helpful to organize all consumers and producers of water to help determine where reuse opportunities exist. Burcu will discuss the pinch analysis technique in a little more detail later in the presentation. By understanding the project drivers and the limit of environmental constraints, we can make better decisions about how to incorporate the utility water scope and identify opportunities to improve the overall design. Process water may take many forms, but it can be thought of as anything that directly contacts process components. It may be used as a solvent to remove impurities or as salts to absorb gases and scrubbers, or it can be part of a cleaning solution for fluidizing other commodities. And it is also used as a feedstock for the process along with many other uses. As we put water in contact with a process, we have to deal with the resulting effluent or process impacted water. The level of contamination and effluent quality will drive the treatment process, whether the wastewater is discharged to the environment or reused in the facility. When it comes to reuse, the cooling tower system is usually the best place where we can dispose the largest amount of water with the lowest quality. So this represents the best opportunity or lowest hanging fruit, if you will. Process water use often results in some amount of water being lost. Losses can be to the environment from evaporation or loss to a product or process waste stream. This slide illustrates the typical water flows through an industrial facility, with evaporative cooling usually being the most significant user. Once the overall requirements of the process and utilities are established, we need to consider the environmental constraints and the practical limitations of water treatment technology. When evaluating water treatment technology, constraints worth considering are cost, water recovery, chemical and energy inputs, and the life cycle of waste produced by the treatment process. Water technology is constantly improving, and it is important to stay abreast of new technology and understand all the potential options available in order to develop the best systems and to function within the legal and ethical obligations of the region. For example, membrane technology has come a very long way over the last 10 years, with significant reductions in cost and improvements in performance. Today, this is one of our go-to tools for treating difficult water problems. Here's an example of a few cooling alternatives to reduce water consumption. As discussed earlier, a significant water demand in many plants is cooling water makeup. This sketch illustrates the three potential configurations that are possible for cooling. The open loop cooling system on the left is advantageous in that it provides the lowest cooling medium supply temperatures, a relatively small footprint for overall cooling duty, and it results in smaller heat exchangers in the process units at the expense of evaporated water. The closed system, shown in the center, will not have water loss at all, the trade-off being usually a higher cooling medium supply temperature, higher power consumption, and potentially greater utility footprint for cooling. On this same same diagram in the center, another variation would be to use an alternate water source, such as seawater, on the heat exchanger instead of air. The direct air cooling process on the right may have space constraints in process units, is not as efficient as water heat exchangers, and is limited to the approach to dry bulk temperature, but it is completely water-free. A hybrid loop shifts heat rejection directly to the air and therefore minimizes evaporation. This may be practical in areas that are water constrained, but the trade-off will be against cost. For water and waste minimization concerns, with this or the open cooling loop method from the first slide, we can minimize makeup and blowdown by using a membrane system to remove hardness or other impurities that cause scale, and returning the permeate to the cooling tower. This may be practical in situations that are constrained by water or waste discharge limitations, but again, the trade-off will be against cost. These are just a few simplified examples of how it's possible to configure the utility system to achieve the desired performance within the project and environmental constraints. For more detailed analysis of water system integration, I'm going to pass the presentation now to Burcu.
Thank you very much, Joe, for summarizing for us why water is such a challenging issue for most industries, giving us such a good example for process design. So far, we have talked about consideration for industrial water. Now we are going to discuss how we can make most of the water available to the industry, and we'll share some of our project execution examples. When we talk about wastewater and water reuse project, the current focus is on end-of-pipe approach. A typical design approach for a new project is to receive the wastewater composition from the plant. And as a water technology expert, we directly start developing a treatment scheme. We need an oil and water separation, a biological treatment, and a tertiary treatment. However, why not take one step back and assess the facility as a whole, meaning production facility together with water system, ISBL together with OSBL. Find out where the wastewater is generated, dive into the details, and find out the value of each stream. As Joe has already highlighted, based on process intensification, we have developed a three-step approach. There are only three steps you should remember. First, minimize. Increase productivity in process and segregate at source. Second, reuse. Decrease resource and energy consumption. And the third one is produce. Generate new product, waste to energy. Let's start with the first step, minimize at source. This example is one of our recent projects from a petrochemical facility. The client provided a wastewater composition, a long list of parameters, and requested us to design a centralized wastewater treatment plant to treat this wastewater stream. A traditional approach to solve the problem would be to consider an equalization tank, CPI oil separator, dissolved nitrogen flotation, biological treatment, and if higher quality water is required, an ultrafiltration and reverse osmosis unit. However, what we have done, actually, we took one step back. We studied the production areas, and we observed that the wastewater actually coming from 13 different units. Therefore, our approach was different. First, we clustered the wastewater stream with similar qualities. The first cluster of streams are one with low total dissolved solid concentration, but with moderate total organic carbon. The second cluster of streams were clean enough for disposal without any further treatment. And the third cluster of streams were ones with high TDS, with little or no organic load at all. In summary, some of streams can be discharged without any treatment. Some of them require oil and volatile organic carbon removal, and some of them require solely salt removal. So with this approach, simply by segregation of waste streams at source, we minimize the overall scope of the project for our clients. As we summarize, it is quite important to take ownership of the water system, identify and analyze each stream, and segregate at source. And we need to really invest improvement projects in the production area. If possible, like Joe explained, we should go back and focus on optimization of factory processes, increase of the efficiency, and focusing on not creating needless waste. That's actually bring us the second step of integrated water solution, reuse. We should not make the common mistake when we talk about reuse. It is not necessary to have a high quality of water for each processes. When we talk about industrial water, there are mainly three different grades. The low-grade industrial water that we use for flushing, irrigation, cleaning of non-production area, and dust control. And to reach this level of water quality, we will need some preliminary units, such as dissolved air flotation or biological treatment. Second one, intermediate grade industrial water. Water that we use for cooling tower and process units. For this level, you need to add some additional treatment units. Of course, it depends on project-specific details. However, we have listed some common combination of treatment units. The third one, high-grade industrial water. Water quality that we need for boiler feed and demineralized water. And again, to reach this level of high quality, you will need to add some additional treatment units, such as ion exchange and advanced oxidation. Saying that, this is just to show you there is already a stepwise approach how we can reuse and define the reuse opportunities. Nonetheless, we sometimes overlook, and again we should take one step back. It is also possible to reuse water and wastewater without any treatment. As Fluor, we apply water pinch analysis, where we identify suppliers and consumers. Then we evaluate the opportunities using water modeling and simulation software. In this way, we can scientifically assess opportunities for reuse. We can find out where to invest in and define lean water investment strategies for facilities. This charts to show a typical pinch analysis for a traditional facility with no reuse. Y-axis shows total dissolved solid concentration, one of the primary components of interest for reuse. On the x-axis, flow is presented as ton per hour. On the left side of the graph, we do list various wastewater streams, suppliers, cooling tower blowdown, scrubber blowdown, process 1 wastewater, and process 2 wastewater. On the other side, there are consumers, processes where we do need fresh water intake, scrubber makeup, cooling tower makeup, process 1 and process 2 water intake. The pinch analysis can be used for larger facilities with many streams. It allows for a graphical analysis to make it easier to see opportunities. The analysis provides a way to show flow versus concentration for each stream, for suppliers and consumers. Wastewater from particular process unit can be considered as a supplier if the quality is adequate for another consumer in the facility, either as is without any treatment or with some treatment. On the right, the graph shows minimum water quality requirements and flows for consumers. As you can see, the scrubber makeup can accept a higher TDS than cooling tower makeup. So this makes it a candidate to receive wastewater from process unit 1 and 2. However, for a cooling tower makeup can receive wastewater from process units number 2 only. A different chart can be made for different components of interest. For example, TDS is one of the primary components of interest, but you can also go along with COD. In this way, we can scientifically assess opportunities for reuse and decrease the total fresh water consumption accordingly. And the last step of integrated water solution is produce. Till recently, when we talk about water and wastewater system, our focus was on pollution control and remediation of wastewater. Wastewater treatment is an energy-intensive process. Of course, it increases the economic burden on industry, as well as carbon footprint on industry and the environment. And the regulatory needs are the primary drivers. However, with energy transition, we are more and more focusing on resource exploitation from wastewater. Waste and wastewater are started seen as a potential feedstock, and we are focusing on waste to produce value-added products, such as bioplastic, biosolids, and biofuels. It is clear that the effort on energy efficiency cannot be delayed. While our focus is changing to energy efficiency, the water challenges that we are facing get more complex and require more attention. Therefore, in the last part of this presentation, we decided to focus on how the water scope is impacted by a process, For this, we have chosen the nexus between water and energy transition. And we have selected co-processing of hydrogenated vegetable oil, HVO, as today's case study, where we will talk about the implication of co-processing on wastewater treatment plant. Before jumping into the details of water and wastewater system, let's take a moment to discuss what is co-processing and how it impacts the existing process units. By following the Renewable Energy Directive 2, refineries will produce fuel from biowaste by revamping existing assets. Fats and oils continue to be the main feedstock for alternative transport fuels. Possible steps to convert biomass to transport fuels: biological, conventional alcohol fermentation or anaerobic digestion, thermochemical, pyrolysis, gasification, and hydrothermal liquefaction. But if we focus on chemical conversion, there are mainly two routes: transesterification, where methanol and caustic are used to produce biodiesel; hydrotreating and hydroprocessing, catalyst and hydrogen are used to produce renewable diesel. HVO is one of these two routes. The difference with the biodiesel is that hydrogen is used instead of alcohol, and the renewable diesel is more environmental friendly and has a longer shelf life than biodiesel. Of course, it depends on the specific needs of each refinery, request on the quality of the end products, availability of hydrogen, and how easy to integrate with the existing refinery units, and the nature of availability of feedstock, which requires also different pre-treatment units. If we look at a typical example of hydroprocessing scheme shown here in the blue, there will be mainly two changes. The first change is pre-treatment. Most feedstock requires a pre-treatment step to prepare them for hydroprocessing. Depending on the quality of feedstock, it may contain different levels of alkali metals, phospholipids, and metallolipids, which can negatively impact the effectiveness of hydroprocessing. Depending on feedstock, pre-treatment will include different steps and may require different utilities, such as bleaching earth and alkaline. The second main change is the reactor. Either the reactor or the reactor beds will be modified. There will be some impacts to the existing facilities. But most important for the water team, a new waste stream to be treated, a higher rate of sour water production that has a different stream composition. When we have an existing refinery connected to utilities, and we are planning to extend our facilities for renewable feed processing, the differences we have discussed for the process will directly impact utilities. Extending our facilities may require the extension of utilities to support the co-processing, of course, depending on the capacity and technology selection. Nonetheless, there are also auxiliary units which will be impacted by co-processing significantly. That we will discuss the second part of this case study. As you can see on the graph, power consumption, high pressure steam, and the boiler feed water will be differentiating parameters. However, I want to highlight that we will be talking about the utility impacts in the renewable fuels webinar. Today, we look at the wastewater production only. It is expected that the wastewater originated from the processing will be at least 10 to 30% of the feed flow. Even though the flow looks quite small, the characteristic of this wastewater stream is not easy to treat in a typical refinery wastewater plant and can cause many unexpected surprises. So, where is this wastewater originated from? Firstly, in pre-treatment step, and then in the hydrotreatment unit, mainly as sour water. Even though the quantity of this wastewater is not that high, and we can compensate with additional hydraulic capacity, The quality of the wastewater makes it more complicated and can cause some unexpected surprises. For example, phospholipids present in water will increase phosphate load. And if there is a discharge limit for total phosphorus, there will be a need for phosphate removal, which is not default part of a refinery wastewater treatment plant. Soap and soap stock, sodium salts of fatty matters present in the wastewater, will cause emulsion and foaming in the wastewater treatment plant and floating biomass. It will significantly wash out the active biomass and will impact the wastewater treatment performance and removal efficiency. So how we can approach these challenges and how to modify our existing wastewater treatment plants. In this figure, again, the blue color represents typical existing refinery wastewater treatment units, whereas the green color represents which units will require a modification or be impacted by co-processing. Processing renewable feeds increase the challenges in wastewater treatment because of high COD and BOD content, high concentration of phosphorus and nitrogen, changing pH, and oily contaminants, and sometimes organic acids or volatile components. These components vary in the wastewater depending on the feed. Palm oil and soya oil produce slightly different components to wastewater. First, you need to treat pre-treatment wastewater separately before blending with the processed water. So there will be an additional anaerobic treatment and dissolved air flotation unit. 100% destruction of soap stock will take place in anaerobic treatment. Then the equalization tank should be modified for the new hydraulic capacity. Biological units to be upgraded for nitrogen and phosphorus removal if required. And the sludge dewatering units should be modified for the new system. It is essential to minimize sludge production in renewable projects. That is one of the main reasons for anaerobic treatment, along with high concentration. Lastly, odor control. We don't show on the scheme, but we should mention odor control as a potential issue for renewable diesel projects. And additional odor removal units may be required as well. So all permit boundaries, effluent discharge, and the sludge disposal should be reassessed. And if you zoom in anaerobic treatment, biogas is the value-added product that we produce out of wastewater. It is clear that a lot of aspects deals with water, even considering HVO co-processing. It is important to have diligently approach to process technology selection and full integration. There are some special aspects, like water and wastewater, that can create some unexpected surprises. And essential to foresee the implication on utilities plus impacts cannot be fixed in the process, should be taken care of in the downstream units. And we need to be conscious on wastewater treatment and permits. Trouble in permitting might also impact the process and production. Before we get into Q&A, let's highlight a few things that we hope you take away with you today. Water stress is a significant risk for projects throughout the globe. Water sustainability is a key component of viability of projects. An integrated water design approach includes 3 key steps to remember: minimize, reuse, and produce. So look at the system as a whole, use process intensification to address problems in an integrated fashion to avoid unexpected surprises. Thank you very much for listening to us. With this, I would like to turn it over to Ellie to start Q&A.
Thank you, Burcu, and thank you, Joe, for the presentation this morning and / afternoon. All right, for the audience members, just a reminder, you can submit any of your questions to the Q&A box, and we'll try to answer as many as we can live here. If we don't have the answer or we need to do more research, or if we can't get to all of the questions, we'll certainly send out a recap after the call. So we do have some questions coming in, and I'll go ahead and start with the first one. And I'm going to send this one to Burcu. So is there another solution to treat pre-treatment wastewater from co-processing units besides anaerobic digestion?
It's quite a good question actually, Ellie, and also interesting one. Of course, it depends really on project-specific details, but if there's excess steam and hot water available, or waste heat recovery system, you can also consider to have a zero liquid evaporation system. And in this way, you can create the concentrates, you can minimize the concentrates, and with high fatty matter content. And you can also have the condensates clean enough. You can reuse in the pre-treatment, for example, the degumming or chloride mitigation units. So, and for this case that we are presented today, we have also evaluated different options, but anaerobic digestion was the most cost-effective option for these clients. But indeed, there are some other options.
Great, thank you. It's a good answer. All right, so we have another one coming in. This question is an excellent question. With the shift to using hydrogen as an energy carrier, how are the hydrogen facilities compared to typical gas processing plants in the amount and quality of water needed? And I think I'll direct this one to Joe or to me, and they may have a response for this one.
Yeah, this is a good question. Fluor does build hydrogen facilities as well as gas processing plants. I really can't answer that question now without going back and looking at the process utilities requirements for these systems. So we're going to have to get back to you unless Tamim has an answer for that. I don't know that he does.
Yeah, Joe, I think what you mentioned is exactly right. We'd like to actually go back to our reference projects and get you more concrete numbers, and that way you'll have a realistic comparison between the two. Obviously, there's different factors that will impact that, but we can highlight that to you in the response.
Great. Thank you, guys. That was a great question. All right. So we have another one that has come in. So zero liquid discharge was not mentioned. When would you consider using zero liquid discharge?
Okay, you want me to take that?
Yeah, go ahead, Joe.
Okay, this is Joe. Yes, zero liquid discharge, for those who don't fully understand what that means, is basically you take your wastewater stream and you eliminate the water and maybe end up with a dry product, so you have no liquid waste. As you might imagine, this gets to be very expensive. There are other options that would be considered minimal liquid discharge, where you can maybe not take it all the way to a dry product. But usually what this involves is evaporation, crystallization, filtration of the crystals, dewatering, and then hauling them off site. You would only want to use this if you absolutely had to. It's not just the cost, but it's an energy component. And if you're worried about your carbon footprint, this is going to weigh heavily into that. So you would use this in areas where you have no options for waste discharge. And there are some places like that. An inland location where all you have are freshwater streams, where people use that water for drinking. The environmental agencies are not going to allow you to discharge very much. So that's probably the best example. If you have an opportunity to discharge waste, then you should use that to the maximum. But where you have too many constraints, then you need to go the other route with a zero liquid discharge or minimal liquid discharge.
Thanks, Joe. All right, so next question. Is it cost effective to use membrane technology on the cooling tower blowdown so we can reuse it as makeup? I think that one should be for Burcu.
It's quite nice question again. Quite interested indeed. Yeah, of course, when we consider like the treated or upgraded wastewater, and especially like the permeate, it's coming from the reverse osmosis. It's definitely a potential source, and we can also use the permeates. Indeed, as it mentioned in the question, we can use as for cooling tower makeup or for process water and for boiler feed makeup water. It depends, of course, the pressure of the boiler system, because the qualities will difference. It will be cost effective, but there are some items we always overlook. The first one is like the permeate oxidation, because permeates contains still some traces of ammonia and some COD and oxygen, and it's quite aggressive actually, because there's no calcium and magnesium, and we call it, because it's so low in the TDS, hungry water. So not directly, but by addition some polishing units, and again I should mention depend of the pressure of the boiler system. Yes, indeed, how cost effective will be really project specific, but the items that I have just mentioned will be the key parameters that we need to take in the evaluation to make sure that this is really cost effective.
Thank you, Burcu. Right, I'm going to direct this question to Joe. In my plant, we purchase water from the local municipality and costs continue to rise. At the other end, we have a limit on the amount of wastewater we can discharge. What should be considered for opportunities to reduce wastewater and lower the municipal water consumption?
Okay, that's a very good question. We've had a few clients with the same situation. The one thing I start off with, like I said in my presentation, I look for the low-hanging fruit, and taking water that's available to me and putting it into the cooling tower for makeup is the first thing I want to look at. What we did on one client, a refinery up in the Midwest, we took the wastewater coming out of the plant. Instead of treating it in a conventional wastewater treatment, biological treatment system, we used what is known as an MBR, membrane biotreatment, which is essentially an ultrafilter. So the water coming out of this wastewater plant is essentially very clean. So we put that, instead of discharging it to the stream, we treated that and sent it back to the cooling tower. That reduced not only the makeup flow rate, but also the wastewater flow rate. And that allowed them to essentially expand their facility, because they were constrained by water up until that point. So, like I said, that's the lowest hanging fruit. Start with that, and then you go back and you look for where's your next consumer that needs water, and how can you get it to them. So that it's basically a method. You can use pinch analysis if you have a complicated facility, but always start with your lowest hanging fruit and what's the least cost, and go from there.
Thanks, Joe. All right, so this next question we've kind of reworded and broken into two questions. So I'm going to try to address this to Burcu, but Joe, feel free to jump in if you have any comments. So should water system design be done in parallel to the process unit design, or should it follow after the process units are scoped?
Oh, this is really good question, because this is also like actually the center of the message that we are trying to give, and I'm really happy to receive this question. Definitely it should be together. I mean, I do believe I am like treating the water system together with the process system is super essential. Like we also have different clients, like one project that clients treated the water package as some kind of package deal or some specific equipment package. And at the end, we end up with the 15 different PFTs because it was equal to one unit in the ISPL. We also have clients that, for example, for PTA wastewater, they wanted to design the anaerobic treatment themselves because they had really high awareness and they really wanted to do have the control of the water system. And for me, I'm total believer if it's affecting your production, and I do believe the water and wastewater is affecting the production units one way or the other, definitely it has to be treated together with the production units at the same time, and totally not to be treated as a package unit or some auxiliary units to the process system.
Yeah, I just want to add one more thing to that. The water and wastewater systems are heavily impacted by permitting, and there has to be an interface with the permitting authorities and what the regulations are and the limitations. So if you don't start that discussion as early as possible, you're going to end up with a lot of surprises, and it's going to change the whole project. It has potential to change the whole project.
Thanks, guys. Thanks for the enthusiasm there. So the second part of this question was, should HAZOP of the water system be done as a segregated HAZOP separate from the unit HAZOP?
It probably, well, what we normally do is a HAZOP on the water system as a separate unit, just like with any other particular unit. Sometimes the water systems will impact the hazard in other areas. For instance, if you lose power, you might lose cooling water. And if you lose cooling water, your reactor may run away. So in certain cases, you've got to look at both. It kind of depends on what you're building. I would hesitate to make just a blanket statement on that.
Maybe I can add on, Joe. I agree with Joe, but I can also give some example from a recent project that we always receive the HAZOP items at the end. But for example, shower water stripper, if you can minimize in one way the ammonia before it comes to the HAZOP stage, because it's also dependent on the production and process improvements, I am favor of, again, maybe not the total scope of the HAZOP. Maybe there should be a separate HAZOP for the water system, but there will be also parts the water or wastewater engineers sit in the HAZOP for different process units. I think it gives such a good impact to close up some HAZOP items before it even became a HAZOP item. So definitely, I would say that there will be some session with it.
Great, thank you guys. All right, so it looks like we're almost at the top of the hour here, so I want to be respectful of everyone's time. So we're going to close Q&A for now, and we will answer the remaining questions in the recap email. So we'll be taking a couple of weeks off from our bi-weekly webinar schedule to prepare new content. So stay tuned for some webinars on renewable fuel production, hydrogen, the strategic application of safety instrumented systems, and advancements in vaccine production from our life sciences team. We're going to continue to announce these events on fluor.com, our social media channels, and through our email notification list. So please continue to stay informed of the events by visiting the Innovation Builders page on fluor.com. If you'd like to subscribe for future notifications, you can email us at innovation.builders@fluor.com with opt-in on the subject line. To our audience, thank you for joining us. We appreciate your attention and thank you for dialing in today. Like I said, we'll send out a compiled list of the Q&As within a few days, and the webinar recording will be available on demand mid-next week at fluor.com. If you do have any additional questions or require information, please email innovation.builders@fluor.com, and someone from our team will get back to you. So from all of us on the Innovation Builders team, thank you again so much for attending and have a safe day.